What I'd like to tell you a bit about today is a journey partially through history and going to some of the most recent results in quantum computation and how they touch back on the issue of quantum control. Very generally, quantum control has a relationship between control and computation that goes very deep down into the dynamics of systems. Here on this slide, I show one set of relationships between how control involves, by and large, the partly known Hamiltonian and the desire to realize a final state in a system. Control is often applied to an open quantum system as opposed to computation, which is applied to a system which you have a great deal of knowledge about and which is artificial. So shown at the bottom of this slide is the idea that you can take one system, a set of spins, and try to use that to mimic another set of spins in the goal of simulating it. And quantum computation has developed a large number of tools, such as the gates and the circuits that Seth introduced to you, to be able to take a known system and make it model a different one. What I'll be speaking about is how these control techniques actually allow us to elucidate and control even an unknown system and make it behave in different ways that allow us to elucidate its behavior. And I'll give you three examples, and I'll begin by giving you one simple one, which reaches back into 1999 and an experimental result then. And this is one based on the idea of quantum error correction, to be able to control and correct for the most basic of quantum mechanical behavior, which is T2. So if you have a qubit, then it will shrink in its Bloch sphere due to the undesired interactions with the rest of the environment. And this loss of coherence can be undone by using quantum error correction. A very simplistic version of this scenario is dealing with just a single spin. And in this case, as I just mentioned, if you consider the following experiment, where we start with an input state shown on the left, where we have a Bloch sphere that is completely round, spherical. Then after sitting in an interaction with an environment for a short period of time, what happens is that the coherence between the vectors in this xy plane get lost. And therefore, the Bloch sphere starts to shrink when you consider its density matrix. And this shrinkage in the xy plane eventually gives you a fixed set of points, which is the vertical set of the line between 0 and 1, which is a statistical mixture that is a purely classical state. So suppose we do this experiment, we would prepare some state which is sitting along the Bloch sphere at a certain angle. We then let it evolve by getting compressed by T2, and then we flip it. At that point, when we measure the magnetization in the xy plane, the length of that vector will tell us how much it is shrunk by. Now, mathematically, this is known as a density matrix being shrunk with the off diagonals, which represent the coherence tending towards 0 in this exponential way shown here. And therefore, this behavior, mathematically modeled as the loss of the off-diagonal coherence in the system, can be analyzed both experimentally and theoretically. So suppose we take a single spin, this loss of coherence theoretically should result in a sequence of measurements as shown here, and experimentally we find a very good agreement with that theoretical prediction when taking a single spin and watching it. So the outermost curve is when you wait nearly 0 time, then as you wait longer and longer, the curves come in and shrink to become this ellipsoid.
Slightly more the projector.
Now, if we, instead of using a single bit, use 2 quantum bits held together, then we can start to use the ideas of information. The quantum bit that we want to think about is a collective degree of freedom between the 2 qubits, and not just a single spin at this point. And when we do this, if we encode by taking the Bloch sphere that's on the left-hand side of this diagram, and turn that into a collective state of the 2 spins, here shown as the 0, 0 plus 1, 1 state, and the 0, 1 plus 1, 0 state. And now the qubits, a collective degree of freedom between those two basis vectors. What happens is that after that evolution, when we decode by tilting the spin back and then measure, we find something completely different in behavior from before. Because this is a code which has allowed us to preserve this spin information in a degree of freedom that is immune to the environmental behavior, or at least allows us to detect it. And here's what one gets. In this particular experimental result, a molecule of sodium formate was used in solution with magnetic resonance to demonstrate what happens. The proton and the carbon-13 spins were the two qubits in this system. And after applying the appropriate pulses, one theoretically expects to find not a elliptical shrinkage, but rather just the Bloch sphere getting smaller and smaller. So there's no loss of relative coherence in this system. This is a beautiful idea of error correction. In this particular case, it's error detection, and the theoretical expectation is very well matched by the experimental ones shown here. What this means in implication is that in magnetic spectroscopy and in the spectroscopy of many other solutions and molecules, whether optically or with magnetic resonance, one can often suffer a loss of signal that will cause a dissipative-like behavior in the spectrum, which is indicative of that elliptical shape of the Bloch sphere I showed earlier. But if one uses this kind of a coding procedure, you can look at many interesting spectroscopic features and have them sharpen up again and not get blurred out. They may get smaller in amplitude if you use this particular code, but by using other codes, you can observe even their amplitude. And that is indicated by this spherical behavior of the Bloch sphere here. Okay. But this is a fairly old example, but it is one which indicates the ideas of quantum error correction moving from theory to experiment in a nice way. Okay, as my second example, I want to illustrate the concept of dynamical decoherence, ability to apply radio frequency to control this spin system. Then a well-known possibility is to turn off interactions between spins. Here shown as a ZZ interaction, which is an easing interaction between two spins. That is a magnetic spin interacting with each other, sees the field of the other spin, therefore has a different energy due to the magnetic field created by the spin nearby. And what this equation shows you is that one can remove this spin-spin interaction by flipping the spin that it's next to for 50% of the time, due to the fact that when you flip the nearby spin, then the evolution of your spin changes sign. It goes around in the opposite direction. And so after it winds up for a little while this way, then when you flip the nearby spin, it unwinds. And by using appropriate periods of time, the net evolution is 0 for the system. And so one can turn on and off undesired terms in a Hamiltonian in this manner. That idea is one of the most important facts that was used in our demonstration of the Shor factoring algorithm, which involved this sequence of pulses shown here. In this diagram, I show 7 different spins vertically, and horizontally, I show the different pulses that were involved in forming this experiment. The 90-degree pulses are shown in red, such as the ones in the upper left corner. And by and large, what you see is a great variety of blue pulses. And these blue pulses are 180-degree pulses, which perform exactly that refocusing, turning off of the interactions that I just described mathematically. And the impact of this back on the field of physics has been amazing. The concept of refocusing has now been extended to be used in other physical systems, as shown in this new graph, work at Sahni, showing its application to the superconducting systems. So a superconducting circuit, such as the one shown here, with a Josephson junction, the large square, allows us to create a coherent state of evolution, where the system evolves rapidly back and forth between 2 levels of the Cooper pair excitation. And as this system interacts with the environment, you can see that there's a decay in the spinning second, which is even more impressive. And this concept of refocusing as dynamical control for systems that are outside of quantum computing has been extended not just to superconductors, but also now to ions and neutral atoms and a variety of other very quantum mechanical atomic and molecular systems. I want to, in this particular case, pose an interesting question to you, because this is a frontier of research. The reason behind why this works is because the sequence of pulses that are applied are known to average away an unknown Hamiltonian, and that is shown here. Suppose one has a Hamiltonian that has an interaction between the system, sigma k, and the environment, E sub k. Then it is well known, theoretically in quantum information, that if one applies this evolution for a while along the x-axis, and then flips it to be along the y-axis, and then flips it to be along the z-axis, then the net evolution turns out to be 0 when you add a little bit of identity to it as well. And that is refocusing generalized to any interaction. What is interesting to me as a question is if there are pulse sequences analogous to this, which average away to interactions that are known but non-zero. And if one were able to achieve this, then you'd be able to create a new approach to building systems that can perform operations robustly, so that they could interact with the theory, for example, of fault-tolerant quantum computation, and allow us to use these ideas of quantum control robustly in other quantum systems as well. Okay, so that is my second example. And now let me turn to my third example of quantum control ideas from quantum computation. This third idea is the notion of composite pulses. And this is a field that is very old in the art of nuclear magnetic resonance, but in terms of quantum computation, it's relatively new. And the most exciting thing here is a recent addition back to the body of work of composite pulses that arises due to the theorems of quantum computing. The example I will give is a description of how this technique can be used to reduce systematic errors. So here's the basic idea. Suppose you have an operation with a certain amount of error. That is, I want to rotate a spin, but every time I rotate it, I over-rotate by a small amount. So instead of rotating 45 degrees, I over-rotate and it's always 10% more. Or maybe I always under-rotate and it's 10% less. And the idea is that there will be a fixed amount of under or over-rotation, but I will not know what it is, because there are so many spins, for example, that I cannot possibly measure all of the calibrations and know how much over-rotation. This problem actually also applies to classical mechanical systems. So, for example, if I have a robot arm and I'm rotating the arm, I may not know exactly how much it is over-rotating or under-rotating. And everything that I described will also be applicable to this classical mechanical system. So I'm describing mathematically this over-rotation in terms of an operator R here, with angle theta being the target. Epsilon describes the amount of over-rotation in a fractional percentage. Now, the solution to compensate for such unknown errors has been investigated in terms of magnetic resonance. And one of the most well-known sequences for correcting for these errors is known as BB1. And the sequence is to replace a single pulse, the Rx theta in this example, with 3 pulses, shown here, followed by the original pulse. So the total sequence here is rotation about the x, a rotation about some intermediate angle and axis angle pi and axis v, and then a rotation rotates. Now I start by going down too far. I rotate past pi all around. Then I rotate past 2 pi all the way around. Then I rotate past again. But as before, I end up very close to where I originally desired to go. And as I mentioned, this works no matter what the initial state is. Now, in the history of magnetic resonance, this level of reduction up to epsilon cubed was the absolute best people could achieve. There was no knowledge of how one could do any better than epsilon cubed. And you can imagine that when epsilon is very large, like 25%, reduce it down to 1%, but that may not be good enough. Suppose you want it down to a tenth of a percent or 100th of a percent because you need very precise movement or operations. Okay, especially when you cascade a large number of operations in sequence. So in the art of NMR, people have searched for better pulse sequences by using computer algorithms to explore the space of possibilities. But the space is enormous. There are far too many ways in which you cascade a sequence of pulses. And it's very difficult to cascade these pulses and still have an operation that works no matter what the initial state is. And here's where quantum computation and quantum information enters. This past year, we were able to develop a sequence of families of composite pulse sequences which correct up to epsilon to the n for any power of n at all. And this is quite remarkable in my view. Here's a sample set of results showing on the y-axis the amount of magnetization that goes to the proper final location, such as the xy plane, as a function of the amount of error in the epsilon, shown on the x-axis here. And with a single pulse, you get this normal cosine-like round shape. With the BB1 pulse discovered by Steve Whitcross, you get a flatter shape that goes up, over, and then back down. But then with these new sequences, you can get arbitrarily flatter and flatter and flatter. Of course, there's a cost. You have to increase the number of pulses. Now, instead of getting flatter so that you decrease the amount of error, it turns out that one of the nicest things about this theory is that you can also reverse it and increase the amount of error. So you can get this sharper and sharper. That is, if the pulses are wrong, then they get even more and more wrong. And this is probably going to be an extremely useful thing for magnetic resonance imaging, where you want to be able to distinguish as much as possible two nearby voxels of space which have different magnetic fields applied to them. Okay. And so we show in this sequence that you get as narrow as you want, and as written at the bottom of the slide, the cost is n cubed. So if you want epsilon to the nth power, the cost is, from a constructive argument in simulations, n cubed pulse length, which is polynomial. And the secret behind how this works is perhaps the nicest thing of all of this theory. These are three equations which are illustrated. Suppose that you have an ideal pulse, which is RB, shown on the right-hand side. Let the actual pulse be this operator M. And what you would like to do is to cancel out the small error in this operator M by adding a small rotation before it that's ideal that just undoes the epsilon part. And how do you create this little epsilon part on the left-hand side is really the heart of the argument. And one can create a small epsilon rotation by rotating around 2 pi with this bad pulse. And this 2 pi pulse will be over-rotated or under-rotated by a tiny amount epsilon. And now you have a basis of small epsilon rotations. So what we know in quantum computing is that if you have the ability to rotate by a small amount, say in x, and a small amount in y, then by combining those small rotations, you can rotate around any axis by a small amount. And that idea is something that was explored by a student that Neil actually picked up as a freshman about 8 years ago, Aaron Harrow. And it involves a foundational theorem in quantum information known as the solidity type theorem. Shown at the bottom of the slide, the equation says that if I have an just the over or under rotation that I showed you. And it is probably going to be quite useful, not just in the art of NMR, but also in rather interesting mechanical systems, which is very unexpected. So I'm going to summarize my talk by giving you two things. In terms of recent progress along this theme, this is one of the nicest experimental results I've seen in recent times. It's a result using the composite pulse that I just showed you, BB1, to electron spin resonance. In the art of electron spin resonance, very few groups have ever applied composite pulses. But motivated by this quantum information result, this group, a collaboration between Princeton and Oxford, applied it to their spin system. And you can see that originally the oscillations, which is the spin coherence of the electron, decreases extremely quickly. But once you apply the composite pulse, then the envelope is nearly flat. It has an extremely long coherence time. All the quantum behavior of the system is now retrieved by using composite pulses. What a beautiful result. And the second thing I want to share with you is that there's also new theoretical progress, which takes indeed a quantum algorithm of all things, the Grover algorithm, and shows how to construct composite pulses from the Grover search algorithm, as if using quantum search as a means of now extracting quantumness from a variety of quantum systems for quantum control. Thank you.